In this video, we're going to talk about polynomial division, which is an algorithm for dividing one polynomial into another in much the same way that we already know how to divide one number into another. Let's begin by quickly reviewing the long division of numbers, which you probably learned at some point in elementary school. This example asks us to divide the number 17 into the number 40. To do the long division, we set up some standard notation. We write down our two numbers with a special division symbol in between them. And then we ask the question, how many times does the number on the left go into the number on the right without going over? A little bit of thought shows that the answer is 2, and so we then write down the number 2 on top of the division symbol. Next, we multiply 17 by 2. That gives us 34, and we write that right below the number 40 and subtract. 40 minus 34 is 6. And now we once again ask the question, well, how many times does 17 go into 6? And this time, it doesn't go in at all. So 6 becomes our remainder. And what we can now conclude, based on this long division, is that 40 divided by 17 is equal to 2 plus a remainder of 6/17. And we have now rewritten the fraction 40 over 17 as a whole number plus a fraction whose numerator is smaller than the denominator. It turns out, rather remarkably, that something extremely similar to this standard long division algorithm can be applied to polynomials as well. Except that this time, instead of dividing a smaller number into a bigger number, we will divide a polynomial of smaller degree into a polynomial of higher degree. This example asks us to divide the degree 1 polynomial x minus 1 into the degree 2 polynomial x squared plus 5x minus 6. Let's see how the algorithm works. We begin by writing down standard long division notation. This time, the divisor x minus 1 appears on the left, and then on the right, underneath our special division symbol, we will write down the dividend, x squared plus 5x minus 6. And we now ask the question, what is the highest power term of the divisor, x minus 1, need to get multiplied by to match the highest power term of the dividend, x squared plus 5x minus 6. See if you can take a second to work that out. The answer is x, and once we realize that, we simply write an x on top of the division symbol. And then what we're going to do is take that x and multiply it by the divisor x minus 1. X times x minus 1 is x squared minus x, and we write that right below the dividend. And, as you can probably guess, we will now subtract these two degree 2 polynomials. We'll subtract term by term. X squared minus x squared is, of course, just 0. Then 5x minus x is positive 6x. And negative 6 minus 0, we can just imagine that there's a 0 there, is minus 6. And now the algorithm continues. We ask ourselves the question, well, what does x minus 1 need to get multiplied by to match the highest power term in 6x minus 6? And the answer is, of course, 6. So we will add a 6 on top of our division symbol. And now we will multiply that 6 by x minus 1 and write down the result. 6 times x minus 1 is 6x minus 6. We once again subtract, but this time we find that after subtracting, we simply get 0. And that signals that we have completed the long division. Indeed, notice that as we move down the line, as it were, the degree of the polynomial that we write down always decreases, and we've gotten to a point where the degree of the polynomial that we've written down, 0, is less than the degree of the divisor. So we can stop. Now, what has this process of long division revealed? It's revealed something rather nice. It's shown us that x squared plus 5x minus 6 divided by x minus 1 is equal to x plus 6 with a remainder of 0. And indeed, that makes sense if you remember how to factor quadratic expressions, because x squared plus 5x minus 6, of course, factors as x minus 1 times x plus 6. And of course, if that gets divided by x minus 1, well, we'll just be left with x plus 6, exactly as we've shown. However, it often turns out that there will be a non-zero remainder, or that factoring the polynomial up top is difficult. And this is precisely when polynomial division is most useful. Let's look at a more interesting example. This time, we want to divide the degree 2 polynomial x squared minus 1 into the degree 3 polynomial x cubed minus x squared plus 4x minus 1. To begin, we once again set up our familiar long division notation. This time the divisor is x minus 1, and the dividend is our degree 3 polynomial, which we write underneath the division symbol. So it's x cubed minus x squared plus 4x minus 1. Now, we ask ourselves, what does x squared minus 1 need to be multiplied by in order to match the highest power term of the dividend? And the answer, once again, is x. So we write that above the division symbol. Now we perform the multiplication x times x squared minus 1 to obtain x cubed minus x. And I'm going to write the x over here to the right so that we subtract without any difficulty. Now, when we subtract these two degree 3 polynomials, we obtain x cubed minus x cubed. Those guys cancel. Then negative x squared minus 0x squared. That's just negative x squared. 4x minus negative x. That's 5x. And negative 1 minus 0. That's negative 1. And now the process continues. What does x squared minus 1 need to get multiplied by in order to match the highest power term in the quadratic, minus x squared plus 5x minus 1? A moment's thought shows that the answer is negative 1, so we will write that down on top of the division symbol. And now we will multiply negative 1 by x squared minus 1, and write down the result. That gives us negative x squared plus 1. And as before, we will now subtract polynomials. Negative x squared minus negative x squared is 0. 5x minus 0 is 5x. And negative 1 minus 1 is negative 2. And we've now reached a stage where the degree of our polynomial is less than the degree of the divisor. Indeed, the degree of 5x minus 2 is 1, but the degree of x squared minus 1 is 2. And that tells us that we can stop the algorithm. Finally, let's step back and make sure we understand what our polynomial division has shown us. It's shown us that x cubed minus x squared plus 4x minus 1 divided by the degree 2 polynomial x squared minus 1 is equal to what exactly? See if you can take a minute to rewrite this ratio of polynomials given our long division. what we've shown is that this is equal to x minus 1 plus a remainder of 5x minus 2 all over the divisor x squared minus 1. And that completes the exercise. Long division of polynomials, as you'll see, is a relatively straightforward algorithm that operates in almost the exact same way as the long division of numbers. And with a bit of practice, you'll be sure to get the hang of it.